Hello all. So in this class we are going to go over to two examples using Dijkstra's algorithm. So here we can also view Dijkstra's algorithm as a single source shortest path problem, meaning that we start from a source node and from that particular source node we are going to find how can we reach in the shortest path from all other vertices. So what are the possible applications of Dijkstra's algorithm? So if you have seen Google Maps, then we see that it gives us 2-3 options where how can we reach from source to destination. And then it is based on time, so how we can reach faster, and according to that we get the maps. Something similar we can do with Dijkstra's algorithm if we can find the shortest path and using Dijkstra, and that can be applicable in different maps. So it is used as a practical application. You can view it as a practical application of Dijkstra's algorithm. So not only maps but other routing systems as well, like in the network, how or whether particular router is located, how the data can be sent, and how what is the best possible ways in which the machines can be arranged or in which the routers can be arranged. So this can also be viewed as a shortest path algorithm, and then the same algorithm can be usable in the network problems as well. So this, as I said, it can be also viewed as a single source shortest path problem because the source node, so all node distances we are going to calculate from a given source node. And so the intermediate path or intermediate vertices for a given path, they also have the shortest distances. Now what is generally input for this Dijkstra's algorithm is a weighted graph G, where we have vertices and edges, and then there is a source vertex. I need to mention which vertex I need to start from, and then I can calculate the respective distances from that source node to other vertices or that node to other nodes. Then what is the output? So from that source vertex, the distance towards all the remaining vertices, it can be seen as the output for the Dijkstra's algorithm. So here is one visualization example of how Dijkstra's algorithm will work in this case. So we know that except the source vertex, all other distances are initially assumed as infinite. So our source in this case is shown as A. So we don't need any distance to reach from A to A. So this distance for the source is initially given as 0. And then all the distances B, D, C, F, G, E are initially shown as infinite. So as we keep on adding the nodes, we can follow the edges going out from that particular node, and then these nodes are becoming reachable. So let's see how it works. So in the first case, what we will do is we will make this node as source node, and so from A we can reach to two other nodes. We can see here there are two outgoing arrows, one is B and one is D. So the distances of B and D will change. So B will become reachable in 2 units from A, and D will become reachable in 1 unit from A. So as soon as we enter A in our cloud or in our known vertices set, so A is now known, and the distance for A is 0, and when we have A as a known node or A is a part of cloud, then we can reach to two nodes, and the distances are updated from infinite. Now we have the distance from A to B is 2, distance from A to D is 1. So here you can see the distances. All other remaining distances will still be infinite. And out of these two, we have to pick the minimum one. So minimum distance we are going to pick at each iteration. So we can see here that distance D is the minimum among these all possible distances that can be reached from A. So the next node that we are going to add in the cloud of known nodes should be D, because that is the minimum distance node that we can reach from. So we added D in the known nodes, and because of that now I have access to some more nodes which can be reachable from D. So we can see that when I know D, I can reach to C in 2 units. So I have 1 unit to travel from A to D and 2 units to travel from D to C. So distance at C gets changed as 3. I can reach from A to D in 1 unit and D to F in 8 units. So this distance is updated as 9. From D to G, it takes me 4 units, and 1 plus 4, I can reach in 5 units from A to G. How about E? E is also reachable now. 1 plus 2, E is reachable in 3 units. How about B? B, we do not create any other path than what we already had. So from A to B, it was in 2 units. Now after knowing D, the path towards B doesn't change because we do not have any outgoing arrow which will take us from D to B. So this path remain unchanged, and these are the new distances that we calculated. So which we can see here, the distance is just the same as I just wrote. So these are the updated distances now. Now every time we keep on adding a new node, we are going to check if we are able to change or minimize these distances. Like how we came from infinite to this distance, it is also possible as we know more nodes, we can have more paths going towards the nodes. So the next node, which node we want to add in the cloud now. So if you remember, the distance to node B is still 2 because it is not changed. So out of this all possible distances, at every iteration we pick the minimum one. So here the minimum distance is B, which is 2, and we can directly go from A to B. So the next node that we are going to pick is B. Now after picking B, again we have 2 outgoing arrows which can go from B to D and B to E. So we will see now, initially from A to D we can reach it in 1 unit, and from A to D and D to E we can reach into 3 units. After knowing B, we have one more possibility to reach to D. We can go from A to B and B to D. But the problem with that is that distance is A to B takes me 2 units and B to D takes me 3 units, which makes the distance as 5. Now certainly 1 is much better than 5, so I am going to ignore this path and the distance is not going to get updated. Any other way or any other node becomes reachable after adding B, we can also reach to E, and that distance is from A to B it is 2 and from B to E it is 10. So that distance from A to E is 12, again not better than what we already have. So I'm not going to add this distance, or I'm not going to consider this path going from A to B and B to E. Instead I'm going to just continue taking A to D and D to E. So these 2 paths will be ignored, and then there is no update of the distances which we already had, and we are going to continue with the same distances. Now what will be the next node that we can add using this particular distances? And we can see that from A, the distance to reach to C and the distance to reach to E both are same, so we can pick either one of those. So let's say we picked E, And again, if I know E, are there any better distances that I am getting? So we can see that from A to D and D to E, it takes me 3 units. After I know E, I can reach to G. So there is only one outgoing edge from E, and that goes to G. So what will be the distance of G after knowing E? It will be 3 to get to E and plus 6 this new distance. So distance, I will just write D now. Distance to G becomes 3 plus 6, which is 9. Now this is certainly not better than the distance we already had. So if we follow the same path A to D and D to G, we can reach in 5 units. And this is not giving me any better path, so I am not updating. If it would have been, then we can change this path. If it will give me something less than 5, then I will change this distance to whatever I get after adding E. But in this case, I am not getting any better path, so I am just ignoring this. And again, there is no updating in this scenario. Now we saw that the distances, if you remember, so after we picked B, the next distance we picked any one of these two, we picked E, and then the next we need to pick is C, because that is the minimum distance that it is giving us. So next node we pick is C. Now after knowing C, is any distance can be updated. So initially we have F at 9 because we were traveling from A to D and D to F, and that was 9. Now after knowing C, I can go from A to D, D to C, and C to F. A to D takes 1 units, D to C takes me 2 units, so A to C basically is 3 and plus this 5. So as we can see here, 3 plus 5 is 8. Now that is less than the initial distance that we have gotten, so now we need to update this to 8. So this, I removed this 9 and I updated F to be 8. Now again we have to compare all the possible distances that we have. So now the distance of F we get is 8, and these two nodes I already covered. So now what is the minimum distance out of these two, F and G? So we can see that G gives me the lowest distance because G has from A to G the distance is 5, from A to F the distance is 8. And again I am going to pick up the node with the minimum or lowest or shortest distance. So I pick G. And again I have to check if, because I picked G, are there any other node become accessible. So from G I have only one outgoing arrow which takes me to F, and I can see that it takes me 5 units to come to G and plus this 1 to reach from G to F. And so the modified distance now for F becomes 6, and initially it was 9, then when I knew C it became 8, and now when I know G it becomes 6, and that is my shortest path to reaching to F, and F will be the last node that we are going to add. So if we have been asked to find the smallest or shortest distance going from A to F, this is how we are going to do it using the shortest path algorithm given by Dijkstra's. So we can see now whatever numbers you see, those are the minimum possible, or those are the shortest path that we need to take, and that those are the distances. So here is another example, similar example, but this is also using Dijkstra's algorithm. So again we saw that the source node has 0 distance and all the remaining nodes distances were infinite. Now as we added the source node. So we want to consider now the source node in our cloud or in our known vertex set. Then we have two nodes become reachable because we have two outgoing edges from A. So we can reach to B, we can reach to C, and then the distance is changed from infinite to the edge, whatever edge takes us from A to B. It takes us 10 units. From A to C, it takes us 3 units. Now out of these two, next time I will pick the node which is reachable in minimum distance, which is C, because C is reachable in only 3 units. So the next node which we are going to add in the known nodes is going to be C. So now C has changed the color and C is reachable in 3 units, and our known vertex set become AC. So now after knowing C, what are the other vertices that are reachable? So we can see that from C we can reach to D, and in order to reach C it takes me 3 units, and from C to D it takes me 8 units. So D is reachable in 11 units. How about E? E is reachable in A to C takes 3 units and C to E takes 2 units. So E is reachable in 5 units. So infinite is greater than these values, and we will replace this infinite value by the new distance values. So which is 11 and 5. Now again we have to find which is the minimum distance out of these 3 nodes. So A to B I can reach. Now after knowing C, I can reach to B as well, and instead of having infinite distance, we need to, so initially we had this distance directly from A to B 10. Now I have another option. Since I know C, I can have 3 to go to C and then 4, because there is an edge C to B which takes 4 units, and it gives me distance 7. So now I will get rid of this 10 and then I will replace it by 7. So let me just erase it. So I will replace this value by 7, and that is visible in the next slide. So all these distances are updated now for B, D, E, and then now I have to pick the minimum distance out of these 3 from A. So the next possible node that I am going to pick up is E, because out of these 3 I have to pick now B, D, E, because A and C are already picked up, and every time we add nodes which are not previously known. So out of these 3 I am going to pick up E because that's the minimum distance. So my vertex set becomes ACE. E has changed the color. Now after knowing E, can any nodes change the distance? We will see. We cannot really go from E to B, so B remains unchanged. How about D? We can reach to D from E. So we can say that till E it takes me 5 units, and 5 plus 9. So 5 plus 9, it takes me 14 units if I know and I want to go through E. So which is not any better than the previous distance I know. So this path I am going to ignore. So we can see that these distances are not going to change, and A to B still remains 7, A to D still remains 11. Again I have to pick up the minimum or shortest distance from these two, 7 and 11, and we will pick B because 7 is less than 11. Now after knowing B, is any possibility that D gets any lesser value? So to reach from A to B, we take 7 units, and we have this edge 2 which we can add, So here now D can be reachable in 9 units if I have, let me write it properly, 9 units if we know B. So this is, so we are going to update this distance of T from 11 to 9. And so this is what we do. We updated the distance from 11 to 9, and that is the last node that we want to add now, and that's the only node remaining, and 9 is the shortest distance that we can take from A to D. 5 is the shortest distance that goes from A to E, and so on. So this is how now all nodes are known and the updated distances are shown with red colors. So C is reachable in 3 units, E is reachable in 5, D is reachable in 9, and B is reachable in 7, and that's the shortest paths which are giving us this particular distances. So if you have been asked for a particular node, what will be the shortest path from A to E, you can say the path which gave you the minimum distance to reach to E. So here we can stop. So I wanted to give you some examples on Dijkstra's shortest path algorithm, and then you can similarly solve some examples given on Dijkstra.